Expedited gate-level verification, unleashing the potential of Netlist integrated emulation platforms. Abstract. The typical design verification process in simulation reliant on RTL provide detailed insights into SoC chipset but may not adequately capture the physical implementation aspect of the implementation aspects and switching activities. To address this, the industry increasingly turns to the gate-level simulation tailored for the specific IP and test features. Despite its tediousness and the high time-consuming nature, thus innovation is critical for efficient SoC design verification, ensuring accuracy and reliability with compromising speed. Gate-level emulation executed in the physical hardware offers faster validation time due to the higher clock frequency in megahertz range, making it ideal for gate-level verification while maintaining the reliability. In this paper, we've introduced the cutting-edge GLE framework featuring custom application-specific integrated circuit ASIC alongside the advanced software test bench for design verification and debugging. Our platform is notably for its optimization techniques, which substantially enhanced efficiency and benchmark its performance against two complex SoCs. Furthermore, we demonstrated this GLE platform's superiority over traditional GLS by highlighting a remarkable execution time improvement of 55 times. Additionally, our test scenarios achieve around 60% greater coverage compared to the conventional GLS. This robust GLE platform is implemented in Cadence Palladium Z2 emulator. In Chapter 1, Introduction. The landscape of the chip development has involved the ever-expanding complexity of the design inherent in myriad SoC architectures, leading to prolonged time frames for bringing the chips to market. Consequently, the validation of SoC functionality post-tape-out has become a time-intensive endeavor. Moreover, the prospects of the SoC fabrication introduced significant bottlenecks that carries substantial financial implications for businesses, regardless of whether the vulnerabilities surface during this phase. To navigate these challenges, pre-silicon verification is of paramount importance in ensuring the functionality, performance, reliability, and adherence to standard of semiconductor chip design before they undergo mass production. Simulators and emulation platforms are extensively leverage in pre-silicon verification to play pivotal roles in rigorously validating SoC functionalities prior to the chip fabrication, thereby safeguarding against potential hazard and enhancing the overall product integrity. The typical pre-silicon verification process in simulation meticulously adheres to an RTL-based approach to analyze and validate the design features of SoC chipset. This technique is highly regarded for its ability to offer an exceptional level of detail, providing deep insight into complex design architectures of SoCs. However, despite the merit, this type of verification method faces vulnerabilities. Specifically, it may not adequately capture the physical implementation aspects and assess the switching activity, which are crucial factors for precise power estimation within the SoC. To address these critical challenges, the industry has increasingly embraced gate-level simulation, an alternative abstraction methodology tailored to evaluate specific intellectual properties, IP features embedded within SoC architectures. Nonetheless, transitioning to gate-level simulation poses its own set of the obstacles. Notably, the process is obstacled with the tediousness and the time consumption, with the verification of even a single test case stretching across multiple days within the simulation environment. This situation underscores the urgent need for innovation and efficiency enhancement in the realm of the SoC design verification, as we strive toward the next frontier of the technological advancement. It's crucial to develop and implement the streamlined strategies that expedite the verification process without compromising on accuracy or reliability. Only through such effort we can fully unleash the potential of gate-level verification and drive forward the boundaries of the modern technology. The gate-level emulation approach stands a paragon of the efficiency and efficacy, primarily owing its execution on the physical hardware infrastructure. Unlike simulation, which have confirmed to operate at lower frequencies in the hertz range, the gate-level emulation operates within the megahertz spectrum range. This significant contrast to the enough clock frequency translates into faster execution and validation times, making it a compelling choice in the gate-level verification arena. Furthermore, the emulation's resemblance to the real silicon ensures that the verification outcomes are not only swift but are also remarkably reliable. We have previously proposed a distinctive GLE methodology employing FPGA emulators hardware, which was published at DVCon in the Conference 2023 as referenced in here. While this implemented approach has effectively tackled some significant issues in the gate-level verification, that is, the duration needed to validate each scenario, yet it has also introduced some drawbacks. Notably, employing in this GLE platform on FPGA-based FPGA hardware has led to a substantial overhead, including prolonged compile times and reduced performance during runtime, particularly evident in the complex SoC and housing the millions of gates. The authors presented a vector mode-based GLE intended for improving the DFT functionality. However, their assessment was restricted to DFT features and smaller SoCs within around 50 million gates. In this paper, we propose a novel GLE platform utilizing specialized hardware components, including the custom-ASICs, in conjunction with a comprehensive software test bench for design verification, debugging, and analysis. Furthermore, a series of optimization techniques and performance strategies are introduced to establish the highly efficient gate-level emulation platform. Additionally, we will conduct a comparative analysis of this efficiency GLE compiled database across a pair of intricate SoCs, an automotive chipset, and an Exynos premium mobile SoC. We will also showcase a range of application scenarios validated on GLE, illustrating its efficacy along with the greater verification coverage compared to traditional GLS. Chapter 2. Gate-level Netlist. A netlist is a functional concept in electronic design serving as a foundational sketch of a circuit connectivity. It outlines the interconnections between the various electronic components such as transistors, resistors, and capacitors, without delving into a physical layout. Essentially, a netlist provides a schematic overview of how components are linked together within a circuit, playing a crucial role in the design and analysis of electronic systems. Similarly, a gate-level netlist encapsulates a circuit's blueprint at its lower abstraction level, detailing its structure using gate-level logic gates. It presents an interconnection between the components using logic gates, and it is typically generated through logic synthesis. Therefore, RTL emulation precedes synthesis, whereas the gate-level emulation follows synthesis, focusing on the finalized gate-level design. Chapter 3. GLE Implementation. A. Implementation Prerequisites. To compile the design files using the incisive compiler, several prerequisites typically need to be met. These prerequisites ensure that the compilation process runs smoothly and efficiently. Here are some common prerequisites. 1. Synthesizer design files and compatibility assessment. Before initiating compilation, ensure that the design files typically written in hardware description language HDR such as Verilog or by high-speed integrated circuit hardware description language VHDL are complete to error-free and adhere to the design specifications. Conduct a thorough compatibility check to ensure the seamless integration of the design files with the incisive compiler and the emulation platform. Verify that a version of the compiler and associated tools align with the project requirements. 2. Primitives and library management. Ensure that all requested SI library, intellectual property, IP blocks, and associative dependencies are readily available and accessible to the compiler. 3. Memory models and phase locked loop management, PLL management. Memory models are usually optimized to a particular technology node cell. Ensure that all the appropriate and required memory models PLLs are synthesized before passing them the incisive compiler. 4. License acquisition. Verifying the availability and validation of licenses required for accessing the incisive compiler and associated emulation platform resources. 5. Resource allocation planning. Strategically allocate the hardware resources on the emulation platform to allocate the anticipated design complexity and simulation workload. Emulation. Evaluate memory like LSF queues and disk space in the processing cores and emulation capacity to prevent resource bottlenecks and ensure timely completion of compilation processes. 6. Robust verification environment. Set up the verification environment including test benches, analysis tools to validate the compiled design against functional and performance requirements. B. Implementation flow. The compilation process comprises several stages aimed at transforming the design source files generated by design tools from the physical implementation into compilation database that can later be downloaded on the emulator. The structure of this compilation database varies based on the parameters set during each compilation step. Additionally, a part of this compilation process is automatically triggered in the simulator to compile the non-synthesized aspect of the design. Later, a swapping mechanism allows for a seamless switching between the simulator and emulator while processing is running. As shown in the figure 1, the generic GLEDB compilation flow goes as follows. Figure 1, typical Netlist compilation flow. As the required design files, module primitive memory models and synthesized analog models mentioned earlier are imported incrementally by defaulting the front-end process of the emulation compiler. This allows for an incremental import approach rather than importing the entire file each time, as only necessary updates trigger the importation. After the parsing stage is done, analysis and abstraction and normalization stage takes place wherein the analysis stage involved performing the various checks, syntax, semantics, and perhaps custom rule checks to ensure the source file's correctness and compatibility with the verification environment. Additionally, this stage might involve the optimizations and transforming to prepare the code for subsequent stages in the compilation flow. In abstraction and normalized stage, the source design is transformed into standardized or normalized form that is suitable for emulation. This might involve mapping complex hardware construct into simpler, more abstract representations, resolving the dependencies and ensuring the consistency across the different parts of the design. An incisive compiler wrapper is the smallest and intelligent tool where the source design is mapped onto specific target resources and also involved dividing the design and into smaller units for parallel processing or distribution across the multiple hardware sources for the synthesis. It also sets up configuring the non-synthesizable logic, test bench initialization, and other parameters to synthesize on the whole hard software environment. So the synthesis phrases the Verilog or VHDL design imported initially into a functionally equivalent GAT-level Netlist or database. The incisive compiler offers an efficient features called distributed synthesis, particularly beneficial for synthesized VHDL or Verilog designs comprising tens of millions of the billions of gates. This feature allows for the distribution of the synthesis task at the module level and dynamically allocating tasks during the runtime to balance the workload across the multiple workstations or the processes. Consequently, this capability enhanced the speed of runtime execution during the design synthesis process. Subsequent to the synthesis phase, a library mapping file is generated. This file serves to establish a mapping correspondence between the physical library paths and a logical directory paths. The follow step is the back-end stage, where the synthesizable netlist produced by the hardware synthesizer is imported to the back-end process precompiled stage. The stage gets rid of the unnecessary task, thereby accelerating the precompile process and enhancing its efficiency. Additionally, various user compile commands such as assigning the net to the certain value and ensuring the signal values implementing the optimizer techniques, partitioning the trial, core or be passed during the stage. Subsequently, the compiler distribution, the workload across the multiple processing unit or cores facilitating the parallel execution of the precompilation process and thus resulting in faster completion. Upon completion, a unified flattened netlist is generated, which is then fed to the compile stage to generate a design database. The final design database is loaded onto the emulator hardware during runtime, along with a switch software test bench for initialization. Furthermore, users have flexibility to switch between the software test bench running on the simulator and DUT during runtime. Number 1. Here's number 2. Number 1. Just FPGA versus ASIC emulators comparison. The table 1 depicted the general GLE compilation flow discussed above and implemented on both ASIC and FPGA emulation platforms. A huge SoC design a reference around 1.5 billion gates. Table 1. FPGA versus ASIC emulators comparison. As is evident from the data of table 1, that while the emulator clock frequency is slightly higher in the FPGA emulation, the compilation time is significantly shorter than an ASIC emulation. Furthermore, ASIC-based emulation compilers provide a superior scalability, integration capabilities, and debugging support compared to the FPGA-based emulation compilers. Chapter 4. GLE Optimization Techniques. A. GLE Compile Time Optimization. In a nutshell, the Netlist design files are passed from the initial import stage and go through the front-end stage. This compilation process resembles basic RTL compilation, where the Netlist file is treated similarly to an RTL file. The Netlist undergoes elaboration and synthesis again during the synthesis stage. However, this generic flow results in a longer compilation time compared to the RTL compilations due to the inclusion of a scan and other search tree, thus creating an overhead. Although there is a reduction in compile time compared to the FPGA emulation compilers, it still remains substantial. We conducted a thorough analysis and devised a strategy to enhance it, leading to the development of the smarter and more effective solutions. Intermittent flow. The incisive compiler offers a user-friendly approach to analysis Netlist files, usually obtained from the physical design or physical implementation team. organizing them into a logical library and referencing the previously analyzed Netlist libraries during the elaboration phase. This analyzed data is utilized by the compiler to extract information regarding Netlist object access and design unit binding. Subsequently, once all necessary information is gathered, the Netlist files are forwarded to the backend tools and the final design elaboration. This mechanism aims to simplify the compilation process for external Netlist with the minimal user intervention. However, it's worth noting that implementing this enhancement results in an additional compile time overhead due to the analysis of specific Netlist files and an elaboration of the required Netlist hierarchy. The incisive compiler leverages compiler Netlist information to import the Netlist modules the following manner as shown in the figure 2. Figure 2. Intermediate compile flow. During the elaboration of the RTL hierarchy, the compiler explores the Netlist definition to identify any unbounded module instances within the RTL. Upon discovering the module within the Netlist domain, it is labeled an important module, accompanied by an information message. For all Netlist modules earmarked for an important, the compiler extracts I/O interface details associated with each module. The Netlist files are passed directly to the incisive compiler stage without undergoing analysis again, bypassing the front-end process. 2. Explicit Netlist flow. As the lists are obtained from the physical design and physical implementation team have undergone prior synthesis, there is no necessity for further analysis, elaboration, or synthesis. Consequently, they can be directly forwarded to the synthesis stage, bypassing both the front-end process and incisive compiler stage as depicted in Figure 3. The Figure 3 is a explicit Netlist compilation flow. Therefore, the Netlist modules containing explicit information can be directly imported, eliminating the need for compiling the Netlist files. This approach, provided by backward compatibility, also serves to mitigate the overhead associated with Netlist compilation. However, since the incisive compiler does not undertake the compilation of Netlist files in this context, it becomes imperative to explicitly finish in the necessary information for importing Netlist modules. Furthermore, under this method, it's essential to explicitly define references to the Netlist object. During the elaboration stage, the incisive compiler employs fake modules to handle instance declaration from before substituting them with the Netlist option. A complete and full list is necessary for proper post-compilation. The ASIC cell library cited by the external Netlist must be compatible with the technology being used. If the cell libraries are RTL format, they need to be converted into GL-level cells through the synthesis. Table 2 illustrates the time taken their respective compilation stages across each mentioned GL flow. Table 2 compilation time expedition across the various compilation stages. B. GL performance improvement strategies. Similar to the compile time overhead caused by the inclusion of scan and other circuitry, there is also significant reduction in the emulator clock frequency, creating additional runtime overhead. This issue been tackled through the following strategy. 1. Oversampling technology. In a fundamental model operation described earlier, each net in the design is refreshed at least once per 2 emulator clock cycles. This means the inputs are sampled at least once per 2 emulator clock cycles, consequently resulting in an output changing once per 2 emulator cycles as well. The sampling happens once per 2 cycles of the fastest clock to ensure the safety operation. Oversampling technology presents the effective means of adjusting the frequency of sampling these inputs and outputs relatively to the emulator clock cycles. The oversampling ratio denotes the number of emulation cycles per cycle of the fastest design clock. This ratio can be configured to a value such as 0.5, 1, or any even odd number. Opting for a smaller value accelerates the design's performance. However, there are potential drawbacks to selecting a small oversampling ratio. A reduced oversampling ratio may lead to higher capacity cost for the design. Some designs may incorporate asynchronous loops, where a small oversampling ratio could adversely affect the functionality of the design. Consequently, it's imperative to carefully consider the select the oversampling ratio to ensure the correct functions of the design. So, Figure 4 illustrates the alignment of the clocks for oversampling values of 1, 3, and 2 respectively. The Figure 4 aligning of the design clocks for a different oversampling ratio. So 2. Adapting the hybrid and stub methodology. Hybrid approach. Let us consider some of our verification scenarios within our purview necessitate the validation of only select IPs within the design at a gate level. Consequently, we have the liberty to exclusively incorporate the design Netlist files pertaining to the IPs that are, while retaining the remaining blocks in their RTL stage before passing them to the simulation compiler. By adopting this strategy, we effectively circumvented the integration of extraneous circuitry and associated netlist overhead, thereby the augmented performance. Stub approach. Another technique involves stub approach, where IPs or blocks slated for validation operate independently without relying on other blocks. Hence, by excluding these IPs or blocks before passing the design to the emulation compiler, we can achieve a remarkable enhancement in the operational speed. Table 3. Depict the achieved operating speed across different smarter solution methods. Table 3. Performance strategies. Applications. 5 applications. The GLE platform accommodates the validation of all zero delay and unit delay GLS verification scenarios. Notably, time-intensive scenarios such as dynamic power analysis and DFT applications and data validation have been considered and executed on this GLE platform. A. Dynamic power analysis. Dynamic power analysis is used to analyze dynamic power consumption due to switching activities in the design, helping to optimize the power efficiency. This is performed using switching activity interchanging format SIFE or SIFE files. SIFE files capture the switching activities of the signal in its design over time, providing detailed representation of the toggle count required for power analysis. B. Scan data validation. In any panic situation of SoC, the user captures output responses and identifies any issues by comparing the observed and expected responses. It is vital in the fault detection and debugging in case of the malfunction of the SoC. Result. The device GLE platform has been implemented on two distinct sets of SoCs and collective risk outcomes regarding the compile time and operating speed post the adoption of the expedition strategies are outlined in the table 4 and depicted graphically in the figure 5. Table 4 is comparison of compile time and operating speed across the two distinct sets of the SoCs. Figure 5 is compiler time and emulator clock frequency post adoption of the expedition strategies. The aforementioned scenarios have been executed the Exynos SoC2 and both GLE and this effective GLE platform with the findings depicted in Figure 6. Figure 6 is scenarios execution summary on GLS and GLE platform. Furthermore, as is commonly acknowledged, GLS verification usually commences after RTL sign-off and it extends until the metal tape-out (MTO) with a relatively short time frame, resulting in achieving only a minimal verification coverage of approximately 10%. If a bug arises post-tape-out, the necessitated a cost accessory spin. In contrast, leveraging this robust GLE platform enhances the verification coverage to around 60% while also reducing overall turnaround time (TAT) significantly. So, the Chapter 7 Conclusion. We propose a cutting-edge Netlist integrated gear-level emulation platform leveraging specialized hardware components such as custom-ASIC alongside a comprehensive software test bench tailored for usage across the different set of SoCs. Additionally, we introduce a range of expedition techniques and the performance strategies to establish a higher efficiency gear-level emulation platform, so significantly reducing the compilation time and boosting the runtime performance. By implementing these strategies, compilation time is slashed by approximately 7 times, and the operating speed sees a remarkable improvement of about 6 times. Furthermore, we showcased a variety of application scenarios validating both the GLE and the GLS platforms, revealing a striking execution time difference of 50 to 60 times and improved test scenarios coverage of 60%. This underscores the efficacy and our approach compared to the traditional gear-level simulation method. Additionally, this implemented GLE platform has been successfully utilized on the 2 different sets of SoCs, with each set performance thoroughly evaluated. So the still limitation and future scope, Chapter 8. The verification of test scenarios is typically performed using zero delay and unit delay Netlist files. As emulators cannot handle the timing or the standard delay format as DF annotations, however, we are currently exploring the feasibility of implementing a hardware mechanism wherein the simulator would handle all timing aspects and the emulator would execute the functional parts. Currently, GLE platform, the Unified Power Format (UPF) integrated two-state emulation platform, have been independently devised and successfully implemented. So therefore, we are now developing a framework to integrate GLE with a 4-state enabled UPF power-aware emulation. This integrated will allow for effective and precise validation of the design power intent, and enhancing the low power verification significantly. The built-in self-test is a technique utilized on electronic devices for self-assessment and eliminating the requirement for external testing apparatus. Thus, the device can self-diagnose and pinpoint the fault overflows to contributing the enhanced reliability and performance. All these various built scenarios can be efficiently validated using this GLE platform. The authors expressed gratitude to the Cadence support team India for their consistent support and guidance throughout the implementation of this efficient GLE platform. Okay, I read this paper today. Expedited GLE verification unlisting the potential of the Netlist integrated emulation platform from DBCon India 2024. Thank you for your time. See you next time.